In the next two units, we're going to discuss information security, mostly network security. So we're going to talk mostly about networks, and specifically in this unit, I'm going to talk about three topics with network security. In this video, I'm going to talk about network security devices. In another video, I'll talk about technologies, and finally, a third video, I'll discuss secure design principles for network security. So let's start with talking about network security, some of the fundamentals of network security. So at one time, and a long time ago, network security was really considered IT security. They were virtually synonymous. So when most people talked about network security or talked about IT security, they were really talking about the same thing. They were talking about network security. The network was viewed as protecting this protective wall that's around our entire network. And as long as somebody couldn't penetrate through that wall, we were protected, and it would keep everything safe. But the problem with that approach is that there's many entry points that can circumvent the network and allow malware to enter our networks, which we've talked about. So we've discussed a lot of the different ways that we can be attacked, and many of them aren't even involving the network. So for example, USB flash drives could be infected that somebody plugs in. There could be malware that comes in through some common protocols, like for example, downloading it through the internet, through the web. Lots of different ways that we can get attack that we may not notice that with network security. So network security has really become just one component of our overall strategy for information security. But again, it's important for us to understand it, and it is still one of the more important areas of information security is network security. So it's certainly something we still consider, something we definitely will always consider with information security. It's an important part of information security. So not all applications designed and written with security and reliability in mind. So we can't fall to other techniques that we've talked about. So yeah, while having anti-malware, anti-spam, and all the other technologies we've talked about, secure coding, which could help us create those secure applications, do a lot of testing to make sure that they're not susceptible. That's not always going to work. So we have to have network security in order to protect ourselves from the cases where some of those flaws may have slipped through the cracks. There's always some chink in the armor that attackers can get through. But our overall strategy in network security, or I'm sorry, I should say in information security, our overall strategy is to layer different approaches to secure our infrastructure. So we may use a lot of the techniques that we've talked about in this course in addition to network security. But network security for sure is a pretty major part of any complete information security strategy. So we do talk about network security actually in two units in this course. I'll discuss it in this unit and in the following unit. So network defense still remains a critical element in any information security plan. You have to have network defenses that prioritize protecting information. So a network security strategy involves network devices, which I'm going to talk about in this video, as well as network technologies that we can use to help protect our networks, in addition to using secure design strategies. So designing our network in a way that is secure. There are some already sort of predetermined ways that we can design our network. People who have done the research and tried different things, and there's certain best practices that we can use, which I'll discuss. So security functions of standard network devices can be used to provide a degree of network security. In other words, we have all of these network devices that we use to support our network infrastructure, and security can be implemented on those devices themselves. So there are things that we can do within those devices to help protect our network. So that's certainly one layer. We can't rely just on those devices, so we still have to use some of the other techniques that we'll talk about in the next unit. So in the following unit after this unit, I'll discuss some other ways to protect our network. In addition to this unit, with technologies, I'll talk about some of the things that we can do. But each of these devices can, on their own, provide some functionality that protects our networks. And I'll talk about some of that. Now, in the previous course, you should have learned about the OSI model. I think I talk about the OSI model. I have a whole slideshow dedicated to the OSI model. I'm sure you've learned about it in other courses as well. The OSI model came out in 1978, was revised in 1983. I disagree with the statement from the textbook that says it's still used today. For the most part, we use TCP/IP today, which we've talked about. So I usually tell my classes that the OSI model is, some textbooks say it's a conceptual model of how networks work, but in reality, it was a standard that was never adopted in practice. whereas TCP/IP is both a model and a standard that has been adopted in practice. And I don't know why textbooks insist on talking about the OSI layers. I think it's because a lot of the certifications still require you to understand the OSI model. But in any event, in reality, in our real world, we only care about TCP/IP. We're not really too concerned about OSI. But these are the 7 layers of the OSI model, which you would be expected to memorize if you were to take any of the certification tests like Security Plus or CCSP, or any of those security certificates that you can get and so forth. But in any event, obviously understanding TCP/IP is far more important in the real world. So the first device that your book talks about is hubs, and I have it crossed out here because no one uses hubs anymore. But hubs were basically a layer 1 device. So they operated at layer 1 of the OSI model. And by the way, layers 1 through 4 in the OSI model are pretty much the same as layers 1 through 4 in TCP/IP. So we can still use that model. It all pretty much works the same. It's after layer 4 when things change, right? Layer 5, 6, and 7 in OSI is really just layer 5 in TCP/IP. But in any event, a hub only works at layer 1, which is really just the wire, right? It's the electrical signaling systems. It's all the protocols that support signaling and so forth. A lot of these IEEE standards that you might hear about are all layer 1 protocols. So a hub is essentially a repeater. So it takes one signal on one port of the device and just repeats it to all the other ports. In the previous course in CT395, which is the first part of this course, or this is the follow-on to that course, I talk about how hubs work a little bit and show you how that works and how it just broadcasts to all of the nodes that are plugged into that device. One of the ways that these hubs can be attacked is through a protocol analyzer. So because it's one device that's broadcasting all the traffic to all of the interfaces to that device, if I'm an attacker and I'm any computer that's connected to that hub, I can see all of the network traffic. All I have to do is load up Wireshark and I can see all the traffic on the network and I can capture it. Whereas something like a switch doesn't allow us to do that. So a switch is a little bit more secure in the sense that it isolates the electrical connections between these different devices. So you're not seeing all of the signaling on the wire. You don't have to ignore traffic that isn't for your computer. You're only getting traffic that is destined for your computer. The switch knows that traffic is going to your computer, and it knows what to filter that's going to your computer. So it's much harder for an attacker to do to sniff the network when you're using something like a switch. Obviously, this is much more common than a hub. So hubs are really not used anymore. Mostly we find switches in most modern networks. They operate at layer 2 in the OSI model and in the TCP model. So it can determine which device is connected to each port. It uses a MAC address, for example, to do that, and it can forward the frames that are sent to that device rather than broadcasting to all devices like a hub does. And as I said, it uses the MAC address to identify all the devices connected to the switch. So a switch is MAC aware, where a hub is not MAC aware. So a hub doesn't know how to deconstruct the frame, whereas a switch does know how to deconstruct the frame. Ergo, it's able to move the traffic to the right port and understand how that signaling needs to be set up between these different nodes that are connected to the switch. So it does provide much better security than a hub by limiting the distribution of frames. So you can still monitor traffic with a switch, and there's a couple different ways to do that. One is port mirroring, which allows the administrator to configure a port to copy traffic that occurs on some or all ports to a designated monitoring port on the switch. So there's a special port on the switch. Well, it doesn't necessarily have to be a special one, but let's say you jack into port 5. You can log into the switch and designate port 5 as the for port mirroring, and then you can tell the switch which ports to mirror to that interface on the switch. And why would an administrator do this? Because they're troubleshooting something and they want to see the traffic. They want to be able to capture that traffic to try to figure out what's going wrong, or why there's some kind of latency, or why there's some kind of issue on the network. So it is important to be able to do that. As well, you can also do network tap, or which could be test access point according to your book, but basically it's a separate device installed on a network that can be used to tap into the all of that traffic. So basically, here's some of the attacks that can be used against a switch. The first one is MAC flooding, which is where an attacker can overflow the switch's address table with fake MAC addresses. So basically, when a device is connected to a switch, it basically has to register its MAC address with the switch using some protocols that we don't really cover in this course, but it has to, and the switch has to maintain that table of MAC addresses, which is an ARP table. So an attacker could overload that switch by giving it a whole bunch of fake MAC addresses, and it's sort of like a denial of service, more or less, but it'll cause the switch to not operate correctly. MAC address impersonation is when you have two devices that have the same MAC address. So if you wanted to, you could basically masquerade as somebody else's network interface, as somebody else's MAC address. In fact, in one of the labs, I ask you to try that. You're going to download a little program called SMAC, and you're going to try to use that to change your MAC address. To be fair, you could just do that in the registry in Windows. You can go in the Windows, and in the registry, you can set your MAC address to anything you want, and it'll use that. It'll broadcast that as your MAC, and it'll register it in the ARP table. So I'm going to have you play with that a little bit. And one of the things that you're going to do too is you're going to look for your MAC address in an ARP table on your own computer, and you're going to see how that can be changed and how that works. And you're also going to play with, in another lab, you're going to play with ARP poisoning. So you're going to see if you can use ARP poisoning. It is hard to do it in Windows 10 because it protects against that much better than older versions of Windows. But you can try it, and it's very ephemeral. You only see it for a short period of time in Windows 10. But you can play with that and kind of see how it works. But basically, it's when the attacker sends a forged ARP packet to the source device, substituting the attacker's computer's MAC address. So you can trick other devices by poisoning the ARP tables. So they'll send you traffic instead of the other device, for example. Port mirroring and network tap, which I just talked about. How would an attacker use that stuff? I talked about how a network administrator would use it, but of course anything that can be used as a tool by a network administrator could also be used by an attacker to attack our network, and port mirroring and network taps are certainly one of those examples. So port mirroring, if you have a port that is set for port mirroring, some switches actually have a dedicated port for port mirroring that you can jack into. Pretty much the only way you can protect against that is to make sure your switch is in a location that there's no physical access from an attacker. That way they can't even try. So even assuming that you accidentally leave a switch connected or something like that, they wouldn't even be able to try to access it. All right, so that's some of the attacks that we might be susceptible to with a switch. So let's talk about routers. So moving up the chain when we go from layer 1, so we went from layer 1 to layer 2, and now we're at layer 3. Layer 3 is routers, which is a network device that forwards packets across multiple networks. So a switch only has context within a single network, whereas a router can move traffic between disparate networks. So it's a much more complicated device. It certainly does a lot more than a switch. They operate at network layer 3. I should say at layer 3 of the TCP/IP model, which is the network layer. They can be set to filter specific types of network traffic. So here we start to see a lot more of the security features that some of these devices might have. We really start to get a feel for that with routers. Routers are sort of a good first line of defense as far as bare metal technology that can try to help us secure our network. In fact, if you go back in time a long time ago, 20 years or so or even more, you'd find that there were a lot of networks that were protected only by routers. So router was pretty much the only line of defense in some of the older networks. And of course, today we wouldn't think of doing that, but just to give you an idea that there is a little bit of history there with routers. And then moving on, we've got load balancing, which moves us up yet another layer. So we move from layer 3 up to layer 4, we can start doing load balancing, and then even up to layer 5. So load balancing is basically technology that helps us distribute work across multiple network nodes. If you recall from the beginning of this course and the previous course, and I've talked about it many times, the CAI, or the confidentiality, and availability, and integrity, those three things are what we're constantly thinking about in network security. So again, I've talked about this before, that it's easy to forget availability. Availability is very important. Load balancing is one of the tools that we have for availability. So there's nothing you can do to absolutely prevent a failure of hardware. We could try as hard as we can. We can have redundancy built into hardware. There's all kinds of things we can do to reduce the likelihood of downtime. We've talked about business continuity techniques and so forth. But it's going to happen, even if it's planned. Sometimes we have to bring down systems. So one of the tools that we have to prevent that type of downtime from manifesting itself to the user is load balancing, which basically allows you to take a single connection into your infrastructure and bifurcate that to two or even to more than two, to redirect the traffic to more than two nodes, so that if one node goes down, another node can take over. Kind of like an airplane with two engines. One engine goes down, the other engine can still fly the plane. It's the same basic idea. So some of the advantages, it reduces the probability of overloading a single server, which is important when we're trying to protect ourselves from denial of service attacks. We can even do load balancing across multiple data centers, across multiple regions. So lots of things we can do to help protect ourselves with load balancing. It can optimize bandwidth of network computers, reduce network downtime. It can be achieved through software or hardware devices. So you can use both. There are services in Windows that can do some degree of load balancing. Windows clustering, if you really want to punish yourself, you can try it. So Windows Server has the ability to do clustering, which is sort of a software that handles this load balancing internally within Windows. And then you have hardware devices that you can put in front of in front of those devices to do the load balancing, and those are much more common. And then some of those hardware devices, really, at the end of the day, they're just running software, but that software is optimized to run on that hardware, just like a router really is just software. But we wouldn't buy. Most of us don't go out and buy a standard computer and run it as a router or a firewall. We buy specialized hardware for doing that, and we talk about that in much more detail in the network security course. So load balancers, so a dedicated hardware device, they're often grouped into two categories. You have a layer 4 load balancer and a layer 7, or really it's a layer 5 in my opinion, because in TCP/IP, which is, I don't know why they always say layer 7, because TCP/IP is only 5 layers and no one uses anything other than TCP/IP. I've talked about that before in other classes as well. So really it's the application layer. So we'll call it that. Instead of layer 7, it's really the application layer. So with a layer 4 load balancer, really all we have to go on is basically the port number, right? So with a layer 4 load balancer or a transport layer load balancer, we look at the port number or what type of service the user is trying to access, and we can load balance the traffic based on that. The problem with only doing layer 4 is layer 4 doesn't have any visibility into the application layer. It doesn't really understand anything at the application layer to make decisions as to where to route the traffic. So where layer 7 comes in, or an application layer device, it can actually look at the payload. It can look at the actual data and try to determine. And I'll tell you a couple different ways this might be used. One of the common problems with load balancers is traffic comes in let's say traffic comes in for port 80, and we're only doing layer 4 load balancing. That traffic on port 80 might go to server number 1. Then that user maybe creates a session with that web server using some kind of session mechanism, which is typically happens in the headers and all that stuff in TCP or in HTTP. So their next request, because the layer 4 device doesn't have any understanding of HTTP, the next request comes in. Maybe it's time for it to go to server number 2 or number 3. So it automatically redirects the traffic to 2 or 3. Well, 2 or 3 won't know that there's a session already created on server number 1, so it forces the user to create yet another session. You could tell that that's probably a relatively kludgy setup for the user, because they have to constantly re-authenticate, for example. And in reality, it just doesn't work. Everybody says this setup is not working right because the users can't get a session. So that's where you would go to something like a application layer load balancing, where it actually understands those sessions. It can see the cookies, and it looks at the header, and it understands that you're trying to create a session. So it knows that all of the traffic for that session should be going to server number 1. And if server number 1 goes down, then sure, it would redirect you. But as long as server number 1 is available, it's going to keep directing your traffic to server number 1 until your connection, until your session no longer exists, it times out or whatever. Then eventually it'll go to another server, perhaps. Now I should tell you that at layer 4, this you can kind of get the same thing. It's sort of a hack to make this work at layer 4. They usually use something called sticky routing, where you say any request coming from a client within a certain period of time it sticks to one of the nodes so it doesn't constantly move it to another node. But usually with sticky routing, you have a finite amount of time that you set that to, and if you exceed that time limit between requests, then it might still go to another server. So in that sense, application still is a better option than using layer 4 load balancing or transport layer load balancing. So whether it's layer 4 or the application layer, we can distribute the traffic in different ways. We can do round robin, which basically says we send all of the connections equally to all the devices just based on the number of the connection. But you can also do it based on the least number of connections to a device. So you can basically the load balancer can monitor the number of active TCP connections and choose the device that has the least number of active connections rather than just doing 1, then 2, then 3, then 1, then 2, then 3, and so forth and so on. You kind of get a sense that if somebody's using one of the servers for a particularly large number of transactions, but then the second user goes to server number 2, and then the third user goes back to number 1, which is already working on a large number of transactions, but now they also have a large number of transactions. Server number 2 is really not going to be that busy. Server number 1 is going to be handling 90% of the workload. So by monitoring those connections, you could get a much better, you can much more evenly disperse the workload as opposed to the connections. So application layer load balancers can also use HTTP headers and cookies and data within the application message itself to make decisions as to how to distribute that traffic. So a load balancer has security advantages. One, they're generally located between routers and servers and can detect and stop attacks. So some of these load balancing switches can add yet another layer to our network security, which is certainly a good thing. And they can be used to detect and prevent denial of service attacks. They can detect them. That's what they're built for. They're built to understand load, right? So they can detect that something isn't right and understand how to mitigate that. And some of them can hide HTTP error pages and remove server information from HTTP. So one of the things about attacks, and we've talked about this before, an attacker typically is trying to do reconnaissance to figure out how, what your infrastructure consists of, because that helps them create much more effective attacks. So a load balancer could help protect from that reconnaissance by hiding that information from the attacker because they're connecting through the load balancing switch. So that's certainly another technique. All right, so a proxy, moving up the ladder here. This is even a little bit more advanced device. So basically a proxy in English is a person who is authorized to act as a substitute or an agent on behalf of another human. But in computing, when we use the term proxy server, it's a computer application that intercepts and processes user requests. Proxy servers have really become an important part of network security. We use them in a lot of different areas now in network security. And a lot of the firewalls that you can buy today, most of them come with some proxy capability that you can use in different ways. And I'll talk about some of those here. So if a previous request has been fulfilled, if fulfilled a copy of a web page, it may be in the proxy server cache, and then the next person who goes to load a web page gets the same version, so you're not constantly downloading content from the internet. So that was really the original purpose of proxy servers, was to save on network traffic. If everybody's going to CNN.com all day long, then why not cache a copy of CNN.com? That way, if 50 people are trying to look at the content of the website, we only have to download it once and we can present it to all 50 users. So, we've already divided our network traffic, by 50 times, which is pretty significant. So that was one of the original purposes of a proxy server. So that's obviously important and helps us with with network security because we have better availability for our networks. So an application-aware proxy is when a proxy server receives requests from a web server and it's then forwarded to the client. Access to the proxy server is configured in the user's web browser, so you have to configure that. And an application-aware proxy might understand the protocol that it's working with. So it might understand HTTP, it might understand FTP, or so forth and so on. So number one, it understands better how to proxy that traffic. But number two, there's features that can help put yet another layer of security in our network and understand, have some context as to what's happening. So again, proxy server, it's another tool in the toolbox. And a lot of the technologies, when you hear about web filtering and email filtering and so forth, most of that is working from a proxy. Usually that's a proxy server that's doing that for you. So some of the advantages of a proxy server is increased speed, which I talked about because it can use its cache. Reduce cost because of the bandwidth that we no longer require. Improve management, so we can block specific web pages and sites using the proxy server, which is a little bit more difficult with some of the other devices that we talked about. Much stronger security. It can intercept malware. It can hide a client's IP address from the internet, and so forth. So definitely some good advantages with proxies, and these are all good reasons to use proxies. One thing your book talks about is the reverse proxy. I think they kind of misrepresent a little bit about how a reverse proxy works in the textbook. Um, in the textbook, they say that it does not serve client, but routes incoming requests to the correct server, which is really kind of like natting, right? So it's very similar to natting, but and they say in the book that the reverse proxy's IP address is only visible to the outside users, and it hides the internal IP. Again, you could just do that with natting. What does a reverse proxy server do for us that a natting doesn't do? So a reverse proxy is sort of like caching data that's inside our network to the outside. So it's the opposite of what we do with a proxy for getting websites from the outside into our network. So it works a little bit different. But again, just like, here's an example of what a reverse proxy could do for us. If we're looking at the application layer in a proxy server for information coming into our network, we could do the same thing for data that's leaving our network. So if I'm looking at that information for data leaving my network, this is how we can do data leakage protection. This is how we can make sure that we're not releasing information that should be protected. That anything, if the classification of data is in a certain realm, then we know the proxy server knows not to allow that data outside of our network. So again, it could be another layer in our network security that can help protect data from leaving our network by using that proxy. So just like we want to prevent bad websites from being viewed inside our network, we can prevent exposing stuff to the web through this reverse proxy in the same way. So it's sort of the inverse of what a proxy server does for internal traffic. All right, so network security hardware. So there are hardware devices specifically designed for network security or designed to do something, like a firewall or a spam filter, VPN concentrators, intrusion detection systems, and finally unified threat management appliances, which basically do a combination or a variety of those things. So a lot of these things I've talked about, a lot of students will tell me, "Gee, Brian, why do I have to go out and buy this expensive proxy server or this expensive router or firewall or what have you? I could build a Linux system and do all of this stuff." And you're absolutely right. Everything that I've talked about so far, you could build a very effective analog to that using a Linux server if you wanted to, which is great. Linux is a powerful tool. It has a lot of free and open source software that we can use to do a lot of things I've been talking about. And really, a lot of those things are the backbone to the commercial products. But the commercial products have hardware that is optimized for what we're doing. And I'll give you an example of that. If you buy a router, for example, if you buy a router for your network, the processor and memory in a router is relatively small when you compare it to a server. And if you wanted to have the same performance that router has with the specialized hardware, if you wanted that same performance with just off-the-shelf hardware that you buy in a regular computer, you would have to have a much more powerful computer to do that. So these companies that make these devices, they know what they're doing. They do a lot of engineering to make sure that they're going to work in the environment, that they have enough, that they have the right hardware, but they don't put any more hardware than they need. So it helps keep the cost down a little bit for sure. And also, they have a supported user interface. They've been tested. They do a tremendous amount of testing to make sure they're going to work the way they're designed to work. So there's a lot of reasons that we should probably use specialized hardware devices. And I'm not saying that you shouldn't go out and build your own Linux server to do all these things. I think it's great to do that, to understand how they work. And certainly if you build your own Linux firewall, you'll have a very good understanding of how firewalls work. So when you do use a commercial product, it'll certainly benefit you. But I would hesitate to say that you can use those in many of the production environments that you'll find yourself in. And maybe you can. There are certainly some that you can, and there are certainly companies that do that, but and organizations that do that. But you certainly have to really know what you're doing to do that. But your book does talk about some of the advantages of using these hardware devices. So a firewall, and really when we talk about network security, firewalls are sort of the cornerstone of network security. It's that central device that almost everybody has a firewall. A lot of the ones I've talked about, you can get away without having all those devices. You can pick and choose which ones you're going to use, but a network firewall is certainly an important part of network security. So it's a host-based application software firewall, can run on a client, for example. You can also have hardware-based, which I just talked about, which is a device that acts as a firewall. But they both essentially do the same thing. They're looking at packets, and I shouldn't say just inspecting packets. A firewall is more than just a packet inspector. It's also looking at the segments, it's looking at frames, it can look at all of that stuff. It can make decisions based on any of the stuff that we find. The only thing firewalls don't typically look at is the application layer. So typically a firewall will be able to decompose the frame, the packet, and the segment, but they typically won't go any further than that. Any device that goes further than that, while it may call itself a firewall, it has functionality that falls more in the realm of, say, a proxy server or a load balancing switch. And that's not to say that firewalls, couldn't do that, but typically when they do, it's because they have that proxy functionality and so forth kind of baked into that device. But basically, firewalls and hardware firewalls usually are outside the network security perimeter as our first line of defense. So typically, the firewall is the first line of defense. In the old days, that used to be the router, but today we put firewalls in that position. So we can filter network traffic, and this is the most common thing we do with firewalls. There's really two types of filtering we do with firewalls: there's stateless and stateful. Basically, stateless is where we make decisions based on what's in front of us right now. That's stateless. So stateless, when I think of stateless versus stateful, I think of the difference between a police officer on the street and a detective, right? So a police officer on the street makes decisions based on what they see happening in front of them at that moment in time. Whereas the detective can take a much more thoughtful approach where they can look at a combination of a lot of things that are happening and make a decision as to what's happening. So a police officer on the street can direct traffic, for example, and say, okay, I've been told that I'm only allowed to let small cars down this road, so when a truck pulls up, they make the truck go a different way. And that would be stateless packet filtering. Stateful would be more like a detective or somebody who's doing some intelligence to say, well, I can let trucks down this road, but I should only let certain kinds of trucks. Maybe I need to avoid letting tanker trucks down this road, or avoid letting certain large trucks that maybe don't have commercial registration or something like that, or maybe we shouldn't let rental trucks down this road, right? So that'd be more like stateful packet filtering. Most firewalls do both, and I can tell you that stateless, why, if they could do both, obviously you're probably thinking, well, stateful packets inspection is definitely a lot better than stateless, right? Makes a lot more sense to do stateful because we have so much more that we can base our decision on. But I would ask you this, if that were the case, how come our police departments aren't made up of detectives, right? Why do we have police officers and detectives? Well, the reason is detectives cost more and they can't do everything. It takes them too long, right? You're not going to have a detective out there looking for people speeding down the highway. You don't have to be a detective to see that somebody's speeding to pull them over and get them a ticket. And it's certainly important for public safety to do this. So we use both. There's an appropriate place for both of these techniques. And if we tried to use stateful for everything, it would make our police department way too slow to respond. And too much would, we'd have to let stuff get through because it simply would be too slow to inspect all those packets. Whereas we can't have a fully stateless police department either, because then we wouldn't be able to investigate those more complicated crimes. We wouldn't be able to do, that more in-depth analysis and intelligence like we can with the stateful. So that's my example of the difference between stateful and stateless. So most firewalls have different actions you can take with packets. You can allow packets to pass through, you can drop a packet, and you can reject a packet. The difference between dropping and rejecting, a lot of people say, well, Brian, that's the same thing, dropping and rejecting. They both don't get passed, right? Well, when you drop a packet, you don't tell anyone. When you reject a packet, you tell the sender, I'm not accepting this packet. So that's the main difference. And again, that just comes back to reconnaissance. If we reject a packet, there's some reconnaissance that can be done by the attacker in that case. They know that it's being rejected. Where if we drop it, it's harder for the attacker to know what happened. Is it a network problem? Is it just not listening on that port? Is it not a valid IP address? And you might be asking yourself, why don't we just drop all packets? Well, that's kind of not the friendly way to do it, right? We should be rejecting actively certain things so that people know that it's being rejected, because we don't want to just pander to the attackers. We have to sometimes do the right thing for applications that are working as designed, that are not trying to attack our network. So it just depends. You have to make a decision. Again, if you take a network security class, they're going to talk in much more detail about those differences and when it's appropriate to use one or the other. Most firewalls are rule-based, which means we write a set of rules that are parsed in sequence. So from rule 1 to rule 10 and so forth and so on. So it'll parse the rules in sequence to make a decision as to what to do with a packet. So rules are stored together in one or more text files that is read by the firewall when it starts into memory, and then it uses those rules to make decisions as it's routing those packets. So application-aware firewalls are a little bit more intelligent than the standard firewall. They can look at the application layer. And again, as I said before, this sort of blurs the line between a proxy server and a load balancer and all of the other technologies I've talked about that work at the application layer. So usually, when I see that a firewall has those capabilities, typically it's doing so as a proxy or something along those lines. So you can have this functionality in the firewall as opposed to having to have multiple devices to do that. Spam filters are another example of an application layer device so a spam filter is basically an enterprise-wide device that you put at the perimeter of the network that's checking both inbound and outbound email traffic. So both SMTP and POP3 typically, although also other protocols like IMAP and things like that. But it's looking at both inbound and outbound to check for spam, and it's trying to either block spam from getting into our network and prevent our network from spawning those spam attacks. So if somebody gets some malware that tries to send spam, usually it will prevent that spam from being spread out to the internet because we don't want to get blacklisted. So spam filters can be installed in many cases with the SMTP server as part of the SMTP server. Your book says it's configured to listen on port 25, but to be fair, most SMTP servers don't listen on 25 anymore. Most of them use the secured ports using TLS or SSL. But certainly this is one of the tools that we have in our toolbox. I have to say, though, it seems like more and more, in my experience, many people are moving away from hosting email on their own networks, and they're moving a lot of this to the cloud. And we're going to talk about the cloud in the next unit in this course. I'm going to talk about how the cloud affects network security and how we're dealing with that in IT security. It's certainly a topic that's not going away, and you could take a whole course about cloud security if you wanted to, but if we offered one. But in any event, the you could have an SMTP server that's filtering that traffic and so forth. And then the next device I want to talk about is VPN concentrators. So VPNs are an important part of doing business today. Everybody has to have VPNs to create these secure connections between different organizations and even between your own organization. If you have multiple offices and things like that, a VPN is a pathway to a secure network on infrastructure that we do not own. And I've talked about VPNs in the previous course. So in the previous, in CT395, we discussed what VPNs are. I talk a little bit about how VPNs use cryptography. They use a lot of the technologies that we talked about when we discussed cryptography. So when you're configuring a VPN, all of that stuff that you learned about cryptography, you're going to use and you're going to see when you create VPN tunnels, for example. There are two basic types of VPNs that your book talks about. There's remote access and site-to-site. Usually remote access VPNs is software to connect a VPN from a remote site, and site-to-site is when we're using hardware VPNs to connect to endpoints. And what is an endpoint? So VPN endpoints are each end of a tunnel for a VPN. They could be software that's on a computer, and they could be a concentrator, which is a hardware device. They may be integrated into other networking devices, so you might see, in many cases, rather than having a VPN concentrator, a lot of firewalls support VPNs. So you'll see this kind of just baked right into the firewall. And I'd say that's probably, for most small to medium-sized businesses, you'll find that the firewall is handling the VPNs. And in large enterprises, you'll find that they have VPN concentrators from companies like Cisco, for example. So VPNs can be software or hardware based. Hardware based generally have better security, they're more reliable, but software based can have a little bit more flexibility in managing network traffic and also where it's installed, because you can install it basically anywhere. The next one is internet content filters, which can monitor internet traffic and block access to pre-selected websites. Again, this is a layer 5 device or an application layer device. Unapproved sites can be restricted based on the URL. They can be restricted based on the content. For example, if the words hate and sex show up in the content, according to the our slide here, although it seems like that'd be a boring place to work where everybody hates sex, right? But in any event, that's content inspection, where it's actually looking at the content in the packet. And then you have malware inspection, where it's looking for malware in those packets. I should tell you though that about the URL filtering, it's kind of a good first line of defense URL, kind of a stateless approach almost. You could think of it as it's fast, it's lightweight, but it's not always effective because people can get around the URL. You can do some spoofing in your host file. That's as easy as spoofing in your host file with a different host name to get around that. So it doesn't always work. So it's definitely good to use more of the advanced tools like the content inspection and malware inspection. So internet content filters. Oh, I'm sorry, I have that in here twice. So web security gateway can block malicious content in real time. It's a higher level of defense by examining content through application level filtering. So examples could be blocking ActiveX controls, which are generally insecure, looking for adware and spyware, peer-to-peer file sharing. If somebody's trying to use your network to use BitTorrent or something like that, which has two problems, right? There's the legal side of it, but also the network performance side of that. Any script exploits, TCP/IP malicious code attacks, and so forth. Some of this stuff could be stopped by a web security gateway. And finally, the last device that we're going to talk about is intrusion detection and prevention devices. So these are devices that can detect an attack as it occurs. IDS systems can use different methodologies for monitoring for attacks. I talked about what an IDS is in the previous class, so you might have to kind of think back about, I talked about heuristic versus fingerprint scanning and things like that, but they could either be installed on a local host or a network. So you have network intrusion detection systems as well as host-based intrusion detection systems. So an extension of intrusion detection is intrusion prevention, which not only detects that intrusion, but can also prevent it from causing any additional harm. All right, so monitoring methodologies, anomaly-based monitoring. You've got signature-based monitoring. So again, that's either heuristic versus signature-based. Very much how, and then behavioral-based. Very much how anti-malware software works. It's the same basic idea as anti-malware as far as these intrusion detection systems and how they work, whether they're host-based or network-based. So a host-based intrusion detection system is a software-based application that runs on the host computer to detect an attack as it occurs. It relies on an agent being installed on the system, which is its biggest Achilles heel because we have to have that installed on the system for it to work. Of course, in a large enterprise, that can be difficult. We have to have that component running on every single machine, every single server. So it can monitor system calls, file system access, changes to the registry or when it's reading from the registry, input and output from the host, so traffic as it leaves and comes into the host. One of the, well, of course, the disadvantage is that it cannot monitor network traffic that does not reach that system, so it has no understanding overall of what's happening in the network. All log data has to be stored locally. It's very resource intensive. It can slow down the system, so people will typically, ask about or try to disable them, which completely defeats the purpose. One of the advantages of HIDS that's not on the slide that I want to talk about real quick is encryption. So a host-based intrusion detection system is able to see the information. It's able to read that data because it's already unencrypted in many cases. Whereas a network intrusion detection system, unless you've got some kind of proxy configured, it may not be able to see encrypted data. So it's going to have a harder time reading the payload of the packet if it's encrypted, for example, if it's in a VPN or if it's an HTTPS connection and so forth. Now, there are ways to get around that, but in my personal opinion, it's not always a good idea to get around that encryption because it breaks one of the important tools that we have for protecting our data, which is encrypting that data to protect it. So it's not always a good idea to break that. It's kind of like walking around the building with a lockpick and just picking all your locks and using a bump key to open up all the doors. What's the point? It's we have that stuff there to protect the building, and we probably shouldn't demonstrate how easy it is to break that stuff. But in any event, that is one of the advantages of host-based intrusion detection systems. Whereas a network-based system, it's running on the network, so it's monitoring firewalls and routers and looking at those log files. It's aggregating all that to some central device which is trying to make some decisions as to what to do with that traffic. So that is a network intrusion detection system. Obviously, the advantage there is that you don't have to install anything on all of the computers. It has a much better view of what's happening across the entire network, more so than the host-based intrusion detection system. So that's certainly an advantage. So an application-aware intrusion detection system, once an attack is detected, a network intrusion detection system can perform different actions to sound the alarm and log the event. Application-aware is capable of some contextual knowledge in real time. It knows about the application. It knows what the vulnerabilities of that application are, and it can monitor for those specific vulnerabilities and have a better understanding of when that's happening. So a prevention system is basically for trying to prevent those attacks. So after we know the attack is happening, an intrusion prevention system is going to try to shut down that attack to prevent it from causing any damage or any harm or loss in data. So the major difference is a network intrusion detection system is monitoring the traffic and raising an alert when something happens, whereas the prevention system is in line. So all the traffic is shunted through the intrusion prevention system, and it can quickly take action to block an attack. All right, finally, we have unified threat management security appliances. Basically, unified threat management, all of these things that I've talked about all these different network devices and each one having its own job. But what if we have that functionality? I kind of touched on this already, right? Like a firewall could also be a proxy server, it could also be a load balancer. So a unified threat management is basically a security appliance that does many, or if not all, of these different functions that we talked about, all from one device. The advantage there, of course, is that instead of having to worry about configuring 19 different devices in different places, you do this all from one unified user interface, and it has context with all of the other layers of security. There are certainly lots of advantages to using a UTM because it has all these different features and functionality that I've talked about baked into one device, which is great. But the problem here is it's one device, right? So when we talk about trying to have layers of security, if your attacker is doing some reconnaissance and they can determine exactly which of these unified threat management devices you're using, then they know what you're using for all of those different pieces. So it might make it a little bit easier for an attacker because they know, they could just try to find that one chink in the armor for that particular device. And it's one of the things that I always think of is it's hard to do everything well, right? We all kind of have our specialties. We all have something that we do well, but it's hard to find somebody that does everything well. Although, you always know that one guy that thinks they can do everything well, right? And that's kind of what these UTMs are. It's that one guy that can do almost everything. But how well all of that stuff is done, I don't know. So I don't have a lot of experience with unified threat management devices other than, I work with network security devices that have, many different functionalities baked into them. And I'll tell you where this usually manifests itself with me is I might be working with a firewall that also has a proxy server, a SMTP, filtering, and it's got, network intrusion detection system that you can license for it. It's got all this other functionality, but I bought it to be a firewall. And I might buy a different device to be an intrusion detection system, some other software and devices, but it also could be a firewall, right? but it's not designed to be a firewall. That's not their core competency. So I still use the firewall device to do that. And likewise, the firewall device's core competency is non-intrusion detection system. So I'm not licensing that module through that particular vendor. But could I do that? Absolutely. I could have it all consolidated in one device. And there are certainly reasons to do that. So in the next video, I'm going to talk about some of these technologies that we have. That's going to be a short video, and then we're going to end with devices, which will be a little bit longer.